You may have seen in lab the effect of debugging being an optional part of the protocol, and I'd like to explore a little bit more about the kinds of debugging information that goes in an executable. As an example, I've set up this program Fibonacci. This is again the recursive Fibonacci, and I'm calling it with an argument of 10. So if we just compile this and run it, then it will work, give us 89 back out. To simulate a bug, I'm going to change the return here to an abort. So that will cause the program to crash if we try running it. Let's look at this in GDB. If we look at run GDB on a.out and run it, then it tells us that the program crashed, but it can't tell us where exactly. It can tell us that it crashed deep in a bunch of calls to fib. So you can see that there's some minimal debugging information that tells us there are function names like main and fib, but if I use up to go up stack frames, then all it can say is now that we're in fib. If I compile the program instead with gcc-g, -g means include more information for the purposes of debugging. And this includes information about line numbers and files, so that this time, when I use backtrace, or just BT for short, then you see it can tell us fib, and particularly it's fib at line 11 or 13. Right? 11 is the one that calls abort. Line 13 is where we have the recursive calls to fib. So that's why we see 11 and a bunch of 13s. And if I go up, then we can see the actual code. So that's the abort, that's the return. And while we're here also, we can print numbers like n. You can see that that information was preserved as well. If I use optimization -O2, O2 says make it go faster in the generally typical ways, and we try running again. We look at the backtrace, and we see that there's similar sorts of information, and in this case it's actually able to preserve n, which is unusual. It's not always able, when you do optimization in general, to preserve that kind of information. If I take this version with debugging information and I run the strip-s program on it, that means throw away debugging information. So if I try again, a.out, GDB of a.out, try running it. I had already run it, let's run it again. And look at the backtrace. We're back to where we were, but even worse, it doesn't even know the names of these functions. It can tell, however, that there was a function that was called from these other functions, and all these addresses are the same because it's the same place where the recursive call is made. The debugger can tell that there are these different stack frames. And the reason it can do that is because using strip didn't actually remove all of the debugging information. If we really want all of the debugging information removed, then we would have to use no asynchronous unwind tables. So unwind refers to that process of showing backtraces. Let's try that variant. So I'm going to use GCC. I'm not going to include -g. I'm going to say f no asynchronous unwind tables. Now when I run GDB and let it crash, when I do a backtrace, you see it's still got some names because I didn't strip away all the names. Even when we didn't use -g, we get a little bit of naming information. But also it's kind of confused about how many stack frames there are. It says, well, something about fib, and then I don't know, and then it goes back to nowhere. Right, that's because we threw away all the information about the shapes of stack frames that the debugger was using before. Right? All it sees is a stack with a big pile of numbers, and it doesn't know where the frame boundaries end. But it turns out there's something we can do to get that back in a different way. I'm going to use f no omit frame pointer. We try one more time and look at the backtrace. We can see we're back to the world where it knows fib is the part that's called. And in this case, it's not because there's extra debugging information. GDB is falling back to a generic method for describing stack frames. And that generic method is to use the RBP register. RBP. So it turns out that RBP has a particular value here that if we cast it to a pointer and look at that, then it gives us the next value of RBP and so on. RBP is going to turn out to be a linked list that chains through the stack frames.